All right, so now we're on lesson 7.4 of reciprocal functions, and it's dealing with part one, which is the rational functions section. So we carry this knowledge from our previous unit, unit 6, which was all about rational equations and rational functions. And so we're really familiar with what rational expressions are and how we deal with them, and potentially some of the outcomes we can deal with them in terms of simplifying them and solving for specific x values. But graphically, I mean, what do these do when we put them into reciprocal functions? And that's exactly what we're going to figure out in this lesson. So when we look at the graphs of, first of all, when we talk about linear functions and the reciprocals, that's what this first example is going to get us to go into. So they're going to give us some input x values, which in this case we have x, but then we're going to have our function of y equals x, which is just a pure linear line of y equals x. And then we're going to take its reciprocal, graph it, and see what this looks like. Now, we know that any sort of regular function can be defined as y equals some sort of f of x, where f of x, it requires some sort of input x value. Its reciprocal function, which is very important to highlight, is where we take 1 divided by that given function, and then this will compare us to some sort of original graph here. Now, if we look at this here, what we're going to do is say, well, if x equals -8, then of course, we're just going to sub in y equals x. That means it's -8. Okay, then we're going to go down the list and say, well, if it's -5, then it's -5. If it's -2, it's -2. And we're just going to go down the list and literally just copy them exactly how we see them, because if y equals x, then the y value and the x value are directly comparable to one another. So we're going to go 1/8, we'll go 0, then we'll go 1 over 8, because if x equals 1 over 8, then y equals 1 over 8. And we just continue all the way down the list here, just basically copying out the exact same thing that we see, because if y equals x, they share the same value. Now, here's where we go into the reciprocal component. From previous grades, or even this grade, Math 20-1, we noticed that the reciprocal is always, you just take the number you see and then you write it over 1. So in this case, we're going to put our x in the denominator, and I'm going to write this as 1 over 8. And then I'm just going to make these as neat as possible and all within the box so they don't overlap. This will be -1 over 5. This will be -1 over 2. We're going to have, in this case, -1 divided by 1, which I'm just going to actually write this out fully, just gives us -1 again. Interesting. Okay, so we want to kind of hold on to this one. And what I would do is when we get to these ones in particular, I want you to actually highlight these two, because we're going to make a special note about these very shortly. Okay, we see -1/2, we take the reciprocal of this. Well, that actually means that it's going to become -2, because we go from 1/2 to then we put the 2 in the numerator. If we take -1/5, well, the reciprocal of -1/5 is -5. Take the reciprocal of -1/8, it's -8. Take the reciprocal of 0, oh, interesting. So now we're going to write this over 1. 1 divided by 0, well, this actually has no solution. In fact, this is undefined. So I want you to write this in here as undefined. Okay, perfect. Now, in a separate highlighter color, what I would do is just highlight this row here, because that's another really important one, is that if we end up dividing by 0, it's undefined, so we can't account for this, and that's going to mean something very particular on the graph, hence why we highlighted it. Okay, if I take the reciprocal of 1/8, this is going to be +8, this is +5, +2. I take the reciprocal of 1 over 1. Well, 1 over 1 is just 1. Another one you want to highlight here, so we're going to make sure we highlight this in green. And I'm highlighting it in green because I want to compare it to the one that was -1. We're going to highlight the one in green here that equaled 1, because if you notice, the two that we highlighted in green, whether it was on the left-hand side or the right-hand side, or whether it was the regular function or the reciprocal function, the value is the same, which is a very interesting kind of thing that we get out of here, or an interesting property. Now, the reciprocal of 1 over 2, reciprocal of 1 over 5, and then lastly is a reciprocal of 1/8. Awesome. Okay, so we have all our reciprocals, we have some special ones that we've highlighted, and now we kind of want to dive into this more, and we actually want to plot these on a graph here. Now, what we're going to do is we're just going to plot maybe 5 of the points, and I'm going to kind of pick them at random here. Let's say I chose the graph y equals x. Well, y equals x, which we're going to plot in blue here. The nice thing about it is that it's actually just at all the 8 and 8s, 7 and 7s, 1s and 1s, 0s and 0s. So the graph actually just goes directly along this diagonal like this. Like I was saying, 1 and 1, 2 and 2, 3 and 3, 4 and 4, and it's a mirror image across the x-axis here going down. Now, what I want you to do is I want you to draw a straight line through this, connecting all the dots. We can put arrows on the end indicating that this goes to positive and negative infinity. And then what I want you to write here is just a specification that says our f of x equals x, or our y is equal to our f of x. Just saying that, like, we have it where some sort of function is defined by this line. Okay, now we're going to do our reciprocal. And we're going to plot, again, just some random points. Let's say x equals -5. -5 will put us over on the left-hand side of the x-axis. 1, 2, 3, 4, 5. And then if it's 1/8 at that point and it's -1/8, that means we can put roughly a dot just below the x-axis here. Now I'm going to put another dot. Maybe we say -2 and 1/2. So that's going to put me to -2 and 1/2. We can put a dot approximately here. I'm going to intentionally put a dot on -1 and 1, which is right here. Interesting, we see that it appears on the same line, which again, we said the ones that we highlighted in green were going to appear both on the original and the new. Now what we're going to do is we're going to choose another point. Let's say I choose -1/2. We go down to -2, so it puts a dot roughly about here. We're then going to put a dot maybe at, if it's -1/5 for x, it's down at -5 for y. So we go 1, 2, 3, 4, 5 down, and roughly about here. Perfect. Now that we have these points, here's what we're going to do. We're going to draw a line that goes through them, connects them, and then we're going to connect it downwards this way. And I want you to put arrows on this side, arrows on this side, indicating that it goes through those points and continues. Now, on the other side here, we can label some more points. So maybe I go to something like 1/5 for x and 5 for y. That's going to put me roughly about a fifth for x, and 1, 2, 3, 4, 5. It's right about here. And then we can go down to another point. Let's say we choose 1/2 for x. That puts us for 2 for y on the reciprocal. So here it is. My one point that was shared between the two was 1 and 1. Then I can go to something like, let's say I go down to 2 and 1/2. Well, that's going to put me down to here. And then lastly, by prediction, if we're at 5 for x, we're at 1/5 for y. And what you're going to notice about these instantly is as soon as we've drawn this and we've drawn this correctly, it's a mirror image across this line here. And so we see that we have this and this, where it's symmetrical along this diagonal line. Okay, awesome. Now let's just provide a bit of a label here. So we're going to say that our y, or in this case, our y is equal to the reciprocal of x, or we could say it's y is 1 over f of x as such. And I just want to match the formatting of earlier. So we're saying that this is our reciprocal function, or that the output is a product of, or is the equation of 1 over that y value, or that original y value. Okay, so now we have our two graphs here. We have our original and our original being blue, our new being red, and we kind of want to describe some general observations of like what's actually happening here when we take a reciprocal of a linear line. Because we had a couple special points in here that we wanted to make note of. What is unique about the reciprocals of -1 and 1? Well, they actually just stay the same value. And so here's what I'm going to say is if we have this, well, -1 over 1 is simply just equal to -1. And if I take 1 over 1, this is still just 1, so the values stay the same. And we want to make a note about this. Stay the same. And these are what we call invariant points. So I'm just going to make that like a little bit of a star note here and say these are invariant points. Perfect. And we should get very familiar with that terminology of an invariant point. It's when we have the value of y that is either plus or minus 1, wherever that is on the graphs here, they're going to stay exactly the same between the new and original, or the original function and the reciprocal function. Now, why is the reciprocal of 0 undefined? Well, suppose we take 0, the number right away, and then we transform it to be the reciprocal, 1 over that number, which is in this case 0. This is actually undefined. And more importantly, we know that the non-permissible value from our previous unit is where x cannot equal 0, because this stems from the idea that if the reciprocal is 1 over x and x ends up being 0, then the non-permissible value, or the value that we cannot include, is 0. And in the 30 level, you're going to notice this leaves a hole on the graph, or it leaves a region in which we cannot cross, or we cannot actually directly hit. We can approach it, but we definitely cannot hit it. Now, for part C, what happens to the value of the reciprocals as the x value approaches 0? Interesting. Okay, so let's take a look at our graph here. If we approach 0, what's happening is that we're looking at it, let's say we look at it from this side. We're approaching 0, we're approaching 0, we're approaching 0, and then it's like, oh, whoa, what happened to the graph? it shoots up in the vertical direction to positive infinity. And then we're like, okay, well, let's consider the left-hand side. I'm coming this way, I'm going towards the zero mark, which would be right here at the origin. I go this way, this way, this way, but then, oh, it diverges away and it goes down to negative infinity. So what we're going to do is our general observation is what happens to the reciprocal of x as it approaches zero? Well, it diverges to infinity. And we want to describe it in the following way here. So I'm going to maybe put a sentence form right here. So diverges to infinity. And we want to get more specific than that. As the x value approaches zero from the right-hand side, what ends up happening is that the y value goes to positive infinity. As the x value approaches zero from the left-hand side, we found that the graph shot down to where y approached negative infinity. Again, as a recap from our previous part here, or if we scroll up here, we were like, if I come from the left-hand side and I'm approaching zero, I go down to negative infinity. If I come from the right-hand side towards zero, it shoots up to positive infinity, and I never actually hit x equals zero. Okay, a bit of an interesting one here. That's kind of revealing something. Now, why does the curve of the graph approach the y-axis but never touch it? Reason is because it's a non-permissible value. So we have a non-permissible value, or we have an NPV at x equals zero. So as it approaches the value of x equals zero, we actually can't have a zero denominator. And the reason is because if x equals zero, it wipes out that denominator. So if we have a non-permissible value, it will only purely diverge away to infinity. Why does the curve of the graph approach the x-axis but never touch it? Very interesting. We look at this and we're like, okay, so all of the red lines here, it seems like they get really, really close. Like they're like pretty much on the x-axis. Same thing over here. And if this graph continued, we'd see it get closer and closer and closer and closer. But again, if we end up having an x value that is something like a really, really large number, even at its largest form, we still get a non-zero answer. And so it will never touch, purely because if we provide some couple examples here, and I'll provide two here. Let's say we choose something like, for example, and I'll put example like this. Let's say we chose 1 over 8. Well, we could say, oh yeah, or let's say 1 over 4 even for this. This is going to be equal to 0.24, or 25, I should say. And even if we chose something like really, really large in this case, let's say we choose something like 1 over infinity, this still does not equal 0. So even as large as we get, it doesn't go to 0. So I'm going to put this here, no matter how large x gets, the value is still not 0. And I'll just short form it as does not equal 0. Okay, let's say, for example, I do the opposite. So let's say e.g., and then I'm going to make the reciprocal 1 over, let's say it ends up being like something like 0.25. Well, this is equal to the following, 1 over 1/4, which then the reciprocal of that is equal to 4, and that's definitely not equal to 0. In fact, if I did something like infinity, this would end up becoming something that is like, let's say I took it as 1 divided by, and I'm going to just maybe arrow over this way, just like we did before, 1 divided by positive infinity, and I'm going to write it as 1 over infinity, meaning it's like a really small decimal here, 1 divided by infinity. Well, this would tend to then be 1 divided by, in this case, 1 over infinity turns this into a positive infinity if I do this double division. And then if that's infinity, then we know it diverged away. So we can say no matter how small x gets, the value will definitely not equal 0, because it's going to be something very large in most cases, or even if it's not large, it will be definitely larger than 0. So no matter which way we go, we can have a small denominator, a large denominator. Either way, it's not going to be equal to 0, and so we're never going to see it cross it. And in fact, this is what we call our horizontal asymptotes of this situation. But we'll get to that. Now, on our graph, I actually want to just draw in a couple things before we flip our page here. can we, in some different color, and you could use this as a highlighter or whatever else you wanted to do, I want you to put a dotted line along the y-axis going up like this. I also want you to put a dotted line on the horizontal because, as you can see, the red graph never crosses either one of these. In fact, it actually avoids these at all costs. It goes to the left to infinity, it goes down to infinity, it goes up to infinity, and to the right to infinity, but it never actually crosses those green lines. And that's very intentional. That is something we need to definitely consider, because we've kind of like we've kind of talked about it a little bit, but not fully. And that's where our next page is really going to dive into this here. All right, let's go to our next page here. Terminology. We have asymptotes, and these break into either vertical or horizontal asymptotes. Now, specifically with this one, an asymptote is something where it breaks up the graph and is a value you can approach, you can get close to, but you'll never actually cross. Now, in the case of a vertical asymptote, these are those vertical lines that when we flip back our page, we'll see our exact example of what we're talking about. Our vertical asymptote is an area in which it occurs for the non-permissible values of the function. So in our previous example, our non-permissible value was x equals 0. If we flip back, let's just annotate that on our graph here. The vertical asymptote, or the one that was up and down that we could not cross if we were the red line, was x equals 0. And so let's just write that on here as this is our, and you can even annotate this in your notes if you wanted, vertical asymptote is where x cannot equal 0. Or I guess we don't want to say cannot equal, but is just equal to 0 because it's the line that defines the vertical asymptote. Okay, now if I flip back here, our horizontal asymptote is defined by the end behavior of our x's here. And so if we look at this, when we highlight this horizontal asymptote, it describes the end behavior of the graph for every very large and negative value of x. So if we go to positive infinity or negative infinity and we realize that x is defined by something where no matter how large or small it gets, it never crosses a specific y value, this is the line that we draw here. And in fact, when we look at this here on our previous page, the horizontal asymptote, or our HA as we're going to call it, I'm just going to write this below, our horizontal asymptote is defined by where y is equal to 0. That's the equation of the horizontal asymptote, or the horizontal line that we cannot cross. Now, again, in this case, the reason the horizontal asymptote exists is because no matter how large or how small x gets, it never crossed this line. In fact, it tended very close to it. And if we saw this on any sort of Desmos graph or anything, it's going to tend really close. It's just never going to actually cross the line. All right, now looking at some characteristics here, let's just describe some of the ones of the original blue graph. Well, on the blue graph, we found that the domain was where x such that x is just an element of the reals. There was actually not really any restriction here. It was pretty open-ended. It went to the left and right to infinity, and there was no sort of horizontal or vertical asymptote associated to the blue graph. Same thing with the range. We were like, okay, well, y such that y is an element of the reals, and it could account for any real number here. As long as it was a real number, it fit the definition. Vertical asymptotes, in the first one, there was none because there was no vertical line that defined this graph. When we just had the blue graph and that was it, the reciprocal had no restrictions. There was no restriction in the denominator because there is none. And we just had where for every y value, there was an x value. Same thing, horizontal asymptote. There is no horizontal asymptote that defined this, so we're going to put none. What's the end behavior near the NPV? Well, there is no end behavior near the NPV because there is no NPV. Now, what is the general end behavior? We said that x can either tend towards positive infinity or x can tend towards positive infinity, or negative infinity, I should say. Because it could either go to the left to infinity or to the right to infinity. Okay, same thing for the y's. Y's could either go all the way up to positive infinity, or the y's could go down to negative infinity. And in our invariant points, what were these? This is where we want to go back and just flip and make sure we're specifying these. The invariant points are the points that occurred not only on this blue graph here, but also on the red graph, meaning it's these points right here. These are your invariant points that we want to account for, and they occurred at positive 1 and 1, negative 1 and 1. So let's make sure we write that in. So we're going to go down to our chart here, and we're going to write in that we have negative 1 and 1, and sorry, negative 1 and negative 1, and then positive 1 and positive 1. Now, if these are invariant points, and for y equals x and y equals 1 over x, they were the same, I want you to just write those in here. We can actually fill that part of the table. if these points do not change, no matter which graph we were looking at, or which of these two graphs we were looking at, not for all graphs, but which of these two graphs we were looking at, then it's just going to stay the same. Now, let's go through the chart for our reciprocal function. The domain. What was the restriction on the domain? If we flip back, we saw that x could not equal 0. And as long as x was not 0, or it didn't pass that vertical asymptote, we said that x can be any real number because it would go to negative infinity or positive infinity. Same thing for the y's. We were like, okay, well, it can't cross that horizontal line of y equals 0. As long as this graph did not equal y equals 0, then it could be any real number in the real plane. So we said YER. Okay, what is our vertical asymptote? Well, we define vertical asymptotes typically in short form as VA. The vertical asymptote was where x equals 0. This was that line that we couldn't cross, and it's purely defined by the MPV because if we look at this reciprocal, x cannot equal 0. If x was 0, it wipes out the whole function and becomes undefined. Now, we look at this here, we go to then our horizontal asymptote, or HA. The horizontal asymptote was defined by where is that y value that we approach but we never hit? It's where it's 0, because we wouldn't want to have a y value of 0. And in fact, we can't have a y value of 0 because it's actually just not physically a possibility in this situation. When we take the reciprocal of all these values, we're never going to cross at that point. So we consider this to be a horizontal asymptote. Now, what is the end behavior near the non-permissible value? Remember that the non-permissible value is our vertical asymptote. And what was the end behavior? It was when y tended to infinity and y tended to negative infinity. So we're going to say our output tended to either positive infinity or our output tended towards negative infinity. Those were the two possibilities. The other possibilities, those are defined on the other spots, but when we're specifically talking about the end behavior near the non-permissible value, or where x equals 0, it tended to go to either positive infinity or negative infinity. Just to show that, let's flip back. If this is where our non-permissible value is, what did the y's do in that region? They either went all the way up to positive infinity or all the way down to negative infinity. Excellent. Okay, now let's go to this table here below. State the reciprocal function, horizontal asymptote, vertical asymptote for each function, and then that will be good for us. So if we know that the reciprocal function is always just 1 over the function that they give us, what we're going to do is we're going to write the first one as the following. We're going to write reciprocal as our output is equal to the original divided by 1, or in this case, 1 divided by the original. Okay, what is our non-permissible value? Well, our non-permissible value comes from the denominator, and in this situation, if we simplified it, we would get an x value equal to 4, or an x value not equal to 4, because if it's a non-permissible value, hopefully it doesn't equal this. Our vertical asymptote is defined by the NPV, so x is equal to 4. That is the line that creates our vertical asymptote. What is our horizontal asymptote? It's where y is equal to 0, or x is equal to 0, not y. X is equal to 0. As long as x is equal to 0, that defines that line in which we cannot cross, that this function will never cross. Okay, let's go down to this one here. So our new reciprocal function will be y equals 1 divided by the original function, which is x squared minus 3x minus 10. If they ever give you a trinomial, factor it. So what we're going to do is we're going to say, if I want to factor this, what multiplies to make negative 10 adds to make negative 3? This is x minus 5 and x plus 2. Perfect. Our non-permissible values come from our denominator. Just like we did in our previous unit, x cannot equal positive 5 or negative 2. If it's either one of those, then it's not going to work. In fact, it would make this undefined. Our vertical asymptotes are going to be at these two locations. So we're going to say where x is equal to 5 for the first one, and then where x is equal to negative 2. And I'm going to make them their own equations because they represent their own lines. The horizontal asymptote, we're going to write it as our y is, and sorry, this should be y equals 2. I don't know why in this original one, I'm looking up above here, we should have y equals 0 because it's the line of verticality that makes this not equal. In this one, we actually have the same horizontal asymptote, y equals 0. Okay, now let's go down to our next one here. This is going to be y is equal to 1 divided by, well, we actually have to factor this thing. To factor this thing, I don't think it's good to put it in the table. It would take too much space. So what we're going to do is we're just going to factor it below here. That's probably our best option. So I'm going to take this trinomial of 3x squared plus 2x minus 8. I can't take a GCF out, so now I'm like, what multiplies to 24 and adds to make 2? Those two numbers would be 6 and 4, so I'm going to put in 3x squared plus 6x minus 4x minus 8. I'm going to factor by grouping, which means I'm going to take out the common factor of my first one. I'm going to take out the common factor of the second one, leaving me with x plus 2. And then finally, which I'm going to arrow up to here, we're going to just finish this factoring off by saying that my two factors are 3x minus 4 and that x plus 2 is the second factor. So this will go in my denominator here of 3x minus 4, and then we're going to have x plus 2. All right, now let's state our non-permissible values. Our first non-permissible value is where x cannot equal 4 over 3. If we isolated it for x, my second non-permissible value is where x cannot equal negative 2. My vertical asymptotes, again, I'm going to write them as their own separate statements. X equals 4 divided by 3, and where x is equal to negative 2. And then in terms of the horizontal asymptote, again, we're going to write y equals 0, because no matter how close our x values get to 0, or no matter how far they get away to positive or negative infinity, the value of that reciprocal will never be 0. And so we're never actually going to touch this line. It's not possible for us. And in fact, like, because we know that it can't go both ways, we just automatically have to assume this. And we could probably assume it throughout the whole unit for the most part. There might be a case or two where this changes, but not for now. It won't be until the 30 level that we really dive into more horizontal asymptotes that are a little bit different. Now, for this one here, we're going to factor this and we're going to write it as y is equal to. I recognize that y equals x squared over 16 is a difference of squares, so I'm going to write it as the difference of squares of x plus 4 and x minus 4. When I write it like this, I get x cannot equal plus or minus 4, and we can just synchronize it or put it all together here. And then what we can do is for this one, because it's the same value and it's plus or minus, you know what, I'll just put plus or minus for my vertical asymptotes. That's totally fine. And again, we're going to do a horizontal asymptote of y equals 0, because in this unit, we're going to look at this and be like, I could go to negative infinity, positive infinity, or as close as possible to 0. And it's always going to just diverge either to positive infinity in terms of the y's, or it's going to get very, very close to the x-axis, but never actually cross like it did in our first example. All right, now, if we're going to sketch these things, we just got to follow a couple rules, and we really want to have our graphing calculator out right away because, and I'll even pull out my graphing calculator on the tablet here, we want to make sure that we have our table of values handy because it's going to simplify our lives a ton. And rather than having to do all this algebra around constructing the table and then having to plot it, we can actually put this together quite nicely. So let's just go over some suggestions for graphing these things on grid paper. First of all, simplify by factoring. I mean, we should know this from before and state our MPVs. Nice thing is we just came off a unit of doing a ton of this with our rational functions and from unit 0. Then we want to clearly identify the asymptotes using a dotted line. So we want to sketch that out right away. Reason is because we don't want to accidentally draw over a spot that we shouldn't. Mark the invariant points where y equals 1 and negative 1, because again, our invariant points are the points that do not change. Very important. And so maybe we should even annotate that here just for ourselves. These are the points that do not change. There we go. Perfect. And I'm a stickler for being a little bit neat here, so I'm going to put that in there. Okay. Make a table of values for the function, which we can do in our calculator, and then just make sure that we take the reciprocal of each of these. So we're going to set it up in our table of values, or we're going to set it up in our table so that we have both the original and the reciprocal function so we can record them all. And then we're going to sketch those two together on the given graph. Okay, let's go through this and we can show all these steps clearly happening at work. So reciprocal function. If our function is f of x equals 2x plus 3, the reciprocal of that is going to be the following. We're going to write it as f of x, which is going to be our function, is equal to 1 over the, and maybe I'll phrase it this way. Y is equal to 1 over our f of x, which is our function, or the original function. In this case, that makes it 1 over the 2x plus 3. And we look at this and we're like, is this factorable? No. In this situation, I can't factor out a 2 or I can't factor out an x, so we leave it exactly like this. Now, what is our non-permissible value? Our non-permissible value comes from the denominator, and it's where x cannot equal negative 3 over 2. as long as x cannot equal 3 over 2, we're like, hey, that works for us. We're happy with this. And in fact, you know what I'm going to do is as soon as I have this value, I'm just going to make sure I sketch it on the graph just to make sure I have an accurate outlook on this. It's negative 1.5. So if I go over to my graph now, at negative 1.5 for x, I'm just going to draw a vertical line, which is right about here. And again, it doesn't have to be the neatest thing in the world. You just want to make sure that it is as close as possible to that value. And then what you can do on your graph is you can write it in. You can be like, this is my vertical asymptote where x is equal to 3 over 2, or in this situation, negative 3 over 2. Okay, now, actually, you know what I might do is I might just write it below. And the reason is because I want to make sure that this graph is as neat as possible as we're constructing it. And so my vertical asymptote is where x is equal to negative 3 over 2. Excellent, there we go. Just so we have it on there. All right, now here's the point that we need to look at in terms of we need to establish what our invariant points are. I mean, we could do this through the table of values, or we could do this specifically with the actual function itself. So what I'm going to do is let's just show it algebraically, and then we can confirm it in our graphing calculator afterwards. If I want my invariant points, remember, if I know that it's y is equal to 1 over, and this is going to be our 2x, and actually we can do this on the original. I shouldn't even be doing this on the reciprocal. I can go y equals 2x plus 3. Where are the invariant points? It's where y is equal to plus or minus 1. So let's do the following two cases. I'm going to label it as case 1. Let's say y equals 1. 2x plus 3. I'm going to subtract 3 from both sides. This ends up giving me negative 2 is equal to 2x. I divide both sides by 2 as such. And I end up getting that my first invariant point occurs when x is equal to negative 1 and y equals 1. So let's just make a note of this. Therefore, our first invariant point is going to be where x equals negative 1, y equals 1. For our second invariant point, we need to consider where y is equal to negative 1, which makes this 2x plus 3. And then this is going to be, we're going to subtract 3 from both sides, which makes this negative 4 is equal to 2x. We divide both sides by the 2. And when we divide both sides by 2, we end up getting that our x value is equal to negative 2, which therefore our second invariant point is negative 2 and negative 1. Excellent. Okay, so now we have these points that don't change. We can actually plot these out right away. Let's go over to our graph here, and we're going to go to our first one, which was negative 1 and 1, which puts us right about here, negative 1 and 1. And then our other one was negative 2 and negative 1, which puts us right here. Now, I can already see the symmetry in my head going on here, but you know, this will take some time to get adjusted to in terms of you'll kind of have to see this as, hey, you know what, in the long scheme of things, you'll see this symmetry, but for now, it's okay. We see one dot on each side of the line, and then we kind of know what the graph is going to look like, but let's construct this here. Now, in your graphing calculator, let's actually type both of these in. In the blue graph, I'm going to type the original, 2x plus 3. On the new graph, which is our red graph, I'm going to type in alpha y equals, so I can do my fraction, 1 divided by the original, which was 2x plus 3. When we graph these, hey, there's what it looks like. Now, the one in red is the one that we're going to plot as our reciprocal. The one that happened to be in blue is the original. Now, we can actually plot this out just very, very roughly. If we look at this, what we're going to do is we're going to go second and then table. This will allow us to get the values. Because we're moving in 0.25s here, this will be good. I actually did this in my tables. I changed my tables to read for every 0.25. And the reason is because I saw in the notes here, we're going by 0.25. So it may actually help us to do that. And I can help you with that within class. So for the f of x, which is the blue graph, we're going to plot that one first. And what I'm going to do is I'm just going to go to all these major points. So at negative 4, and actually we could plot these simultaneously in the sense of on the table we can put them in. When x equals negative 4, the y value for the first one was negative 5. If we put in negative 3, this was negative 3. For my reciprocal, the reciprocal of the first one was going to be negative 0.2 from our chart, which is the same as negative 1/5. So maybe I'll just put it in as 1/5, because if we know the first value, we know the other one. This is going to be negative 1/5. The reciprocal, the next one, is negative 1/3. In your calculator, it might give you decimals, but if you get whole numbers for your original, just take the reciprocal of that, which means put in the denominator. Now, let's go to our next value, which is negative 2. So I'm going to scroll down until I see that. Negative 2 means we have a negative 1, which then keeps as negative 1. And again, this was our invariant point. So what I'm going to do is I'm actually just going to highlight this row because that represents one of the invariant points. I'm then going to go down to 1.75 or negative 1.75. which is just a touch bit higher here. So 1.75 gives us negative 1/2. So I'm going to just tuck that away for a second. This is negative 1 over 2. The reciprocal of that is negative 2. 1.5 gives me 0. The reciprocal of this is undefined because you can't define, or you can't divide by 0, so undefined. Then we're going to go to 1.25, which is positive 1/2, and its reciprocal would be 2. We then go to negative 1, which has a, in this case, our negative 1 should just give us 1. I don't know why it's not showing there, but we're going to put in our 1 here. There we go. So again, this was our other section, which was our, not our reciprocal, but it's going to be another one of our invariant points. So that's our second invariant point. And then in terms of, let's just grab that there. When we go to 0, which is down here, there we go. When we have 0, it gives us our y-intercept of 3 on the original. Reciprocal of 3 is 1 over 3. And then for positive 1, which we're going to scroll down here, we end up getting 5, which its reciprocal is 1/5. Okay, use the table of values to do exactly what I said. I wouldn't do this all algebraically. It's going to take way too long to do that. Okay, let's go through this, and we're going to start plotting all these points. We're going to make this one our blue graph. We're going to make this one our red graph. And I shouldn't make them both blue or else that's going to be a little confusing. So this one's blue, this one's red. All right, the original is in blue. Let's plot some points. -4 and -5. So that's going to put us somewhere off the graph, so maybe I won't plot that one. -3 and -3, which puts us right here. Our next point was -2 and 1, which puts us right here. Hence, it's an invariant point because the red and the blue both match. Let's say I put another point here, which would be our, let's say we choose, I want to use the whole numbers just so that to keep it easy. -1 and 1, so that puts us at our second invariant point. We have 0 and 3, which puts us up here. And then that's probably all that we can fit on the graph that we could actually see. So I'm just going to connect them with a line, put an arrow on the end, and then be like, hey, you know what? This is our original y equals f of x. And let's make sure we note that. Especially when you're graphing these things, I think it's important to make sure you're consistently labeling, because if you don't label, it can be very easy to get off track here. Okay, y equals f of x. Now, we're going to do the same thing, but for the reciprocal. We know our first 2 points, which were the invariant points. We then want to go, well, if x equals -3, then at -3, it was -1/3. That puts us somewhere like roughly about here. If x equals -1, then this is at +1, which puts us here. So that's our second invariant point. Let's say we chose where x equals, I don't know, -1.5. Well, -1.5 gave us 0. So that was about here. Oh, that's why, because it's going to cross our horizontal asymptote, and we don't want that. So this should be out of there. And then, actually, no, we can keep it at 0. Sorry, my bad. We're going to keep it at 0. Let's say I have x equals -1.25. This is going to be where it's a half. So I can put 1.25, and this is going to be a half, which is down here. So like somewhere here. Let's say I chose something else like -2. -2 put us at the invariant. Let's say I go to, I wanted to figure out if I had any other values here that were going to be close enough, but it doesn't look like it. So let's say I go to -4, then the reciprocal is -1/5. So that's going to put me over to 1, 2, 3, 4, somewhere like right here. And then on this, the nice thing is we can actually start approximating in the sense of, if we know that we have these values, which are like, we know our vertical asymptote is at -1.5, then yes, this is why it would be excluded here. I should have known that -1.5, if that's our vertical asymptote, it's out of there. So that's perfect. This one, I'm just going to redo this point here and see if we have any other additional values. It doesn't look like we have anything that would be super helpful other than at 0, we know that our reciprocal is going to be 1/3. So I'm going to go down to like here. For 1, we have 1/5, which puts us down to like very close to the x-axis. And then if this is the general pattern, well, what I want you to do is I want you to just sketch over this in the red. We know that it's going to look something like this. Connecting the red through, it's going to go down and then go to infinity. And I just kind of want to redraw that second section because I want to get as close as possible to that -1/5, but not actually cross it. On the other side, same thing. I want to go up, 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 up to positive infinity, and then I want to go down here and then get very, very close to the x-axis, but not quite hit it. And this one in red is the graph that we consider to be our y is equal to 1 over the f of x. Perfect. And then I'm just going to tidy this one up a little bit. This is our y is equal to f of x. Awesome. Okay. So now we have our reciprocal, we have our original, we have the table for it. And then this one, I'm just going to put a circle and a line through it, indicating that we cannot consider it because it is our MPV or a vertical asymptote. Now, again, what is the horizontal asymptote? We can actually put a dotted line here and say, put dot, dot, dot all the way across. It's where y equals 0. And so I might include this in here and be like horizontal asymptote, HA, where y is equal to 0. Perfect. Just to make sure that we're seeing this for what it is. Awesome. Okay, scrolling down, our asymptotes. We know our asymptotes right away. They come from the NPV and where the x cannot cross the x-axis. So we see this as our vertical asymptote, or VA, is where x cannot equal, or x is equal to 3 over 2. I always tend to confuse it with the NPVs in terms of like cannot equals and equals, but just make it equal to because we're defining a line. The horizontal asymptote, or the HA, is where y cannot cross 0, because no matter how large the x value, no matter how small, it's never going to cross this line of y being 0 as the horizontal. Its domain, well, specifically with the blue one, we don't want to really comment about that one. We want to comment about the red domain. The red domain is the following. We're going to write domain, or D, x such that x cannot equal that negative 3 over 2, because if it does equal to the 3 over 2, then we're going to cross our vertical asymptote. If, as long as it's not the vertical asymptote, we say that this is an element of the reals. Perfect. Now we're going to do our range, and maybe I might have to shuffle this over just a tad here, just to give us enough space. So there's my domain. My range, which I'm going to try to condense in here, or R, we're going to say, well, as long as y does not equal 0, then this is defined for any real number. In fact, this can be an infinite amount of solutions as long as the y is not equal to 0. And again, these come from those dotted lines, or like those invisible boundary lines that the red graph cannot cross. All right, now one pattern I want you to recognize as we move forward in this unit is if you're given a linear line, the inverse of the linear line, or not the inverse, but the reciprocal to be more specific, will always give you something that looks like this, where if the original graph is a diagonal like this, its reciprocal will have these kind of two bent and kind of reflected, if you want to say, parabolas from each other in a way. I like to call them parabolas. They're not necessarily parabolas, and they shouldn't be considered parabolas, but if we have this linear line, you see them as it kind of crosses those invariant points and then bends away, crosses through those invariant points, bends away, where the linear line can be drawn right through both of them at kind of their, like, if you want to say like their middle points, if you want to draw it that way. Okay, now that gives us one problem here. So if we have a linear line and it's reciprocal, that's how we would define it. Now, let's say we go to this one here. So now we have a quadratic. Instead of a linear line, we have a quadratic, and we want to put this all together in terms of its reciprocals. Right away, let's do the reciprocals. If the f of x, or the y, is equal to x squared minus 4, let's make sure we write this in its factored form. We're going to write the y is equal to 1 over f of x, which is 1 over, we see this as a difference of squares. It's going to be x plus 2 and then x minus 2. Now, what does this mean the MPVs are? The MPVs are where the denominator would become 0. Our first MPV is where x cannot equal negative 2, but then x can also not equal positive 2, because if it's either positive 2 or negative 2, the whole thing disappears in terms of it becomes undefined. What are the invariant points? Again, our invariant points come from where y is equal to 1 or negative 1. So let's just take a second to algebraically solve this. If I write 1 in for that y, well, this is going to become 1 is equal to x squared minus the 4. I add 4 to both sides. This is 5 is equal to x squared, which means that x is equal to the plus or minus of the square root of 5. Okay, our other invariant point is going to occur at the following. And I guess I should put this together as a point, because that's not a point if I write it in that way. I'm just going to kind of move this up as much as I can and then put the point below. Therefore, the point that makes the invariant point is 1 being the plus or minus of square root of 5. There we go. Our second invariant point occurs where it's -1, which is equal to, on this one, I'm going to write it as x squared minus 4 again. I add 4 to both sides, making this 3 equals x squared. And if I take the square root of both sides, this gives me that x is equal to the plus or minus the square root of 3. And now I want to write it as therefore we have it at -1 and the square root of plus or minus 3. There we go. Now, writing plus or minus 3, we might have to edit this very shortly because realistically, the invariant point might only occur at one spot. Maybe it occurs at both, but it depends, right? And it depends on what function we're considering. And for some of you, you might be like, wait a minute, plus or minus, like why could there be a plus or minus? I think you'll see very, very shortly what happens to this graph. Okay, now our asymptotes, we could write that in afterwards. In fact, what we're going to do is we're going to start plotting in these values right away. I'm going to go to my graphing calculator and go y equals, we're going to clear out our original functions we were dealing with, and I'm going to write in x squared minus 4, and then I'm going to put in our reciprocal, which is alpha y equals 1 over the x squared minus 4. Graph it. There we go. Whoa, look at the graph we just constructed. And here's where it sheds a little bit of light on why there's an invariant point that includes multiple points, or I shouldn't say multiple points, I should say 4 points. If you zoom in on this graph here, how many times do the blue and red graphs cross each other? And you would say a total of 4 times. Hence why we have the plus or minus. And in fact, here's what we're going to say about our invariant points. There is 4 invariant points because the plus or minuses do matter. One of them is going to be 1 plus the square root of 5. The other one is 1 minus the square root of 5. And same thing for this one. So there is actually 4 invariant points that we want to make sure we list. And in fact, we could do that right now if we really wanted to. Let's just exit this for 2 seconds. We're going to calculate the value roughly of the square root of 3 just so that we have it. So square root of 3 is this. Square root of 5 is going to be equal to this. So 1.73, and it's the plus or minus of that at -1. So let's go to -1, which is going to be here. And then we're going to go to 1 point, I just want to make sure I get that decimal right, 1.73 negative. So that's going to be roughly about here that there's an invariant point. And then if we look at the positive version, it's going to be roughly about here. So there's our first 2 invariant points. Our other 2 invariant points come from the 1 plus or minus the square root of 5. So I'm going to pull this back up and be like square root of 5 is 2.23, meaning at +1, I'm going to be somewhere up around and I want to make sure I get this right here, x equals 1, it's going to be plus or minus 5 in terms of this one here. So I'm going to have here, and then 2.25, which is down here. Perfect. Oh, and then I wondered why something was off here. Okay, this is where we got to be very careful. When we put in our points here, I need to make sure I put my plus or minus in terms of the x value. I was wondering why this seemed a little off with the graph. I need to pay attention to these things, right? Very, very easy to slip up on these. So plus or minus 5, and then 1, and then this one is going to be actually the opposite as well. So we're going to write this as the x value is going to be plus or minus the square root of 3, and then this one is going to be our -1 here. Now this should make sense because when we go to plug this in on our graphs here, it's going to look like the following. So in terms of the x values, the first x value that we're going to work with is we're actually going to plot these two here. We're going to take the square root of 3, which again is 1.73. 1.73 puts us about here, and then we're going to go to -1, which is about here. We're going to do that for plus or minus, which puts us here and here. Here and at -1, which is about here. There we go. And then let's do our other 2 points, which come from here. We're going to go to plus or minus the square root of 5, which is 2.23. And we're going to plot those. So 2.23 for x is about here, and at +1, which puts us about here. And then our 2.23 and +1, which would put us about here. There's our invariant points. Okay, this is going to make a little more sense for us now. All right, now I'm going to open up the table of values here, and we're going to plot in as many points as we possibly can, but the ones that match up to here. So in our first graph, we want to look to where it is -3. So I'm going to just scroll up. And again, we're in 0.25 mode. The reason is because I see that we're kind of moving in intervals of 0.25. So I'm going to hold on to that. First one, if x equals -3, y is equal to 5. The reciprocal of 5 is 1 over 5. Very easy. -2, we're going to scroll down. It gives us 0. And obviously, we know that the reciprocal of 0 is an undefined value. So we don't want to put anything in there. 1.75 gives us negative 0.937. And then in terms of its reciprocal, this is going to give us negative 1.066. There we go. If we go to 1.5, this is 1.75 or negative 1.75. If we wanted to, we could be like 1.75, do math frac, get our value of 7 over 4. So that would be, if I go back to my table here, and I want to go to the exact value that we were at. If this is for 0.5 and we ended up getting that it was negative 1.75, this gives us negative 7 over 4. The reciprocal of this is negative 4 over 7, because we keep the negative. We go to 1.25, which puts us at 2.43. And some of these numbers are not really pretty, but that's totally fine. If we can make them pretty, we will. Otherwise, just don't worry about it. 0.41. When it's negative 1, it gives us negative 3, which the reciprocal is negative 1/3. If it's 0, which will be up here, it's negative 4, which its reciprocal is negative 1 over 4. If we get 1, which is down here, we get negative 3. And we get, that means negative 1/3. If we have 125, it gives us the 2.43, which then its reciprocal is 0.41. If we get 1.5, we get that same value again of negative 7 over 4, which again by its reciprocal is equal to negative 4 over 3. Negative 4 over 3, negative 4 over 7. I was like, seems a little odd. 175 gives us negative 0.937, which that reciprocal is 1.066. If we get 2, we end up getting a 0, which means that it is undefined. Okay, so again, this is why you do the table of values, because would I expect you to start doing these things all algebraically? Absolutely not, because this is a lot of work to construct if you don't have your table of values. Now, we're going to plot out all the ones that are like easy numbers, because if we don't plot out the ones with easier numbers, then it's going to be a little tough. And again, this is all approximation. So your graphs just have to be decently close, but like as best as possible. Now, let's actually draw in our MPVs, or our vertical asymptotes, right away. Our vertical asymptotes come from the NPVs, which are plus and minus 2. So I'm just going to draw a vertical line here. And again, you're seeing the symmetry across the lines, and positive 2. Here are the vertical asymptotes. And if I have enough space, it's going to be a little tight here, but let's say I have x is equal to 2 down here, and I write x equals negative 2. That will be okay. Formally, I would like to write in a VA there, but that will be okay. So we actually know, and we can fill this information in here, our vertical asymptotes occur when x is equal to plus or minus 2. Our horizontal asymptote in this year is just going to be primarily where y is equal to 0. So if we wanted to draw that piece in, we also could do that as well. And I'm going to actually do that right away. I'm going to be like dot, 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 because we know no matter how close this graph gets to y equals 0, it's not going to cross. Now what we're going to do is we're going to draw the original parabola in the middle here. So we have all the values we need, or majority of the values we need. If it's negative 2, it was 0. So negative 2, and I'm going to draw this one. Let's say I draw this one in blue, and then I draw this one in red just to organize it. Then if I draw this, it's going to be at negative 2 and 0, which negative 2 and 0 puts me right here. It's going to be at negative 1 and negative 3. So that's roughly about here. It's going to be at 0 and negative 4. It's going to be at 1 and negative 3. It's going to be at 2 and 0. And then we could just roughly draw in that parabola here. So I'm going to just kind of like provide as best of a sketch as I can. There we go. And then it would go up like this. Same thing on the right-hand side. We would draw it up, and then it would go kind of like this. Perfect. It may go a touch wider, but we're generally okay with this for the most part. Okay, now here's where we want to draw our what's happening when we take these. And in fact, I want to just give you the indication here that you can actually draw these in very, very nicely without even a table of values. If you look at this, like before we even consider the table of values, what is a reciprocal doing to all the y values? If y equals like positive 5, then what's the reciprocal of 5? 1/5. So it would put us down here. What is the reciprocal of 9? Oh, it's something like 1/9, and it gets lower and lower and lower. What if I took the reciprocal of a really low y value, something like 1/5? Well, the reciprocal of 1/5 is something like 5. The reciprocal of 1/9 is 9. So as we take really small values, like such as 1/5, 1/6, 1/7, the reciprocals of those become large. And the large values become small. Hence, we can actually sketch this in quite nicely without even looking at our table of values that accurately. I mean, if they ask us to sketch in points, that's one thing, but or and specific points, but otherwise, what we can almost do is the following. I'm just going to sketch it in like this. We're not going to cross there, and we're going to go all the way up to positive infinity. So, such as this. We then have our middle values. If it's positive or -4 for the y, -4, the reciprocal of that is 1/4. So I'm going to put my dot here. The reciprocal of 3, that's 1/3. It's going to put me here. The reciprocal of 1/3 is going to put me here. Oh, look at this. We can kind of see the pattern where it's forming this interior shape where it won't cross where it goes to the green lines, but our small values become large, our large values become small, and it fills this out. And if we know this is all symmetrical, again, we can go on our other side here and fill this out where it demonstrates this graph here. So again, small values become large values become small values because reciprocal is literally flipping the value. Now, if we look at our graph here, and our graph that we just constructed, do these not look quite similar? In fact, they do. The only thing I would edit about this graph is that my graph in the blue should just be a little bit wider. So maybe I make an effort to do that here. I don't know how easy this is going to be, or if it will destroy the graph. Maybe it does, but I think it might be important just to draw this out a little bit wider. I'm going to make an effort to do this here. So let's say I draw the blue graph just a little bit wider, like so. And then I draw the blue graph just a little bit wider again. There we go. Now I'm going to sketch in my green just to fill in what I might have taken away. I'm going to fill back in the red graph accordingly, like so, and like so. There we go. And then this kind of looks more accurate, where our original parabola is a little bit wider. And then we can see, again, I just want to really get this point across here. If we have large original y values in terms of like a large integer value, then in the new graph, it becomes a small integer value, or a small value. I should not say integer, but a small value. If it was a really small value, something like right here near the x-axis, well, really small fractions, when you take the reciprocal, become very large values in the red graph. So you can basically sketch it in that following way, where it's like small x or small y value, big y value, large y value, small y value, and just being able to sketch this in based on this. Now, this establishes two different shapes that we now have. Before we complete this problem and kind of talk about domain and range and all that good stuff, if you look at the shape of what a parabola looks like, this is very common. And in fact, the only difference would be is if it's an inverted parabola, it would just change a slight bit in terms of it would have the shape of this same thing, but then almost flipped. If we look at the linear graphs, they always look like this. So it's not like these are dynamically changing from one problem to the other. They'll always follow the same very similar shape. Just depending on the problem, it will just impact exactly if they're going to look like a line like this instead, or if they're going to look like the one here. And then very similarly over here, we could have it where it's like, oh, this inner part is where it looks like it has this inner U, and then the outsides are like this. But that occurs if it's a reflection or if there's a vertical reflection about the x-axis. More on that when you get to your practicing or further examples. Okay, domain and range. Our domain is restricted by the vertical asymptotes. So we have to account for this and say x such that x cannot equal plus or minus 2. As long as x doesn't equal plus or minus 2, it can be any real number in the plane. We then look at our horizontal asymptote to determine our restriction on our range. Our horizontal asymptote said that our y value cannot cross where y equals 0. If it's y equals 0, then it will approach that value, but it won't actually cross. And then we say y is an element of the reals. Excellent. Okay. Now, this covers two types. We've now done linear graphs, we've done quadratic graphs. But now we want to do potentially a quadratic graph, but only with 1, 0 to see what these look like. 1, 0 again, meaning one x-intercept. And these are our perfect square trinomials. So let's write out our reciprocal. If our original function is this, y equals x minus 2 squared, the reciprocal of this is where we say y is equal to 1 over, and because it's already in its factored form, we don't have to do any sort of factoring, which is actually kind of nice. There we go. What is our MPV? Well, it's the restriction of the domain, what x cannot equal. In this situation, x cannot equal 2, or else the denominator becomes 0. What is the invariant points? We're going to say, well, 1 occurs when y equals 1, and so this is x squared minus 1, like this, or x minus 2 squared equals 1. If I square root both sides, square root of 1 is just plus or minus 1, which is equal to x minus 2. And then the following cases can apply here. So if we know that it's going to be this plus or minus 1, then we have it where we are going to add 2 across, and we're either going to get where x is equal to, let's say it's the plus case. Plus 1 plus 2 is going to give us x equals 3. The other case is going to be where x equals negative 1 plus 2 is going to be positive 1. So the 2 points that we could get out of this, and this is going to be a little bit squishy. That's why it's a little bit tough. Okay, let's say I put it right there. Then therefore, our 1 point is going to be where x equals 1 and y equals 1. The other point is going to be where x equals 3 and y equals 1. Okay, then we're going to do our other case where if it's equal to negative 1 instead, negative 1 is equal to x minus 2 squared. Well, if I square root both sides, oh yikes, this is not good. If I square root this side and square root this side, we cannot square root a negative. This doesn't work. Square root of negative 1 does not exist, or DNE. And if it does not exist, then we're not going to consider an invariant point where y is equal to negative 1. This would be bad. So our two invariant points are going to occur at 1 and 1 and 3 and 1. All right, what are the asymptotes? Well, just like we've talked about before, the vertical asymptote is always the x restriction, or the NPV. So vertical asymptote is where x is equal to positive 2. Just to double check, positive 2, yep. Our horizontal asymptote for this year at least is going to be where y cannot equal 0, or specifically, it's the line that defines y equals 0. If we say cannot equal 0, then it's like, although it's not going to hit y equals 0, hence it's technically not equal to it. When we describe an asymptote, it's a vertical line or an imaginary line that creates some sort of division on this graph. Now, what we're going to do is we're going to go over and fill in our table of values for this one here. Realistically, we could probably do some of these algebraically, but again, it's going to be way faster just to go into your calculator and do this. So I'm going to type in the original, which was in brackets, x minus 2, close the bracket, all squared. Then in the reciprocal, it's going to be alpha y equals 1 over, in brackets, x minus 2 all squared. We're going to graph this. Whoa, okay, this is kind of an interesting one. We see the two graphs pop up here, but before we do that, let's do our second table. Let's see if we can fill in some of these values here. I'm going to go down to where our value is 0, which means I actually have to go the other way. Perfect. Let's scroll up to 0. Okay, so if x equals 0, our first value is going to be 4, which means the reciprocal of that is 1/4. If we go to 1, which is going to be down here a little bit, just scroll down, it's going to be 1 and 1, which was actually one of the invariant points. We should know that. So I'm just going to highlight this because that's an important value. It's one of our invariant points. We're going to go to 1.5, which gave us a quarter, or 0.25. Reciprocal of that is 4. We go to 2, which gives us 0, which means the reciprocal is undefined, as we've seen before. If we go to 2.5, well, there's actually not a value here. And the reason is because this might actually be one of our restricted values, or it might have some sort of value that we cannot cross here. This is going to be 4. We go to 3, which puts us to 1 and 1, because again, this is one of our invariant points. So I'm just going to tuck the calculator away, highlight this because that's our other invariant. And then I'm just going to bring it back one more time. And I want to go to where it's 4, which gives us 4 and 4, or 4 and a quarter. So this one will be 4. This one will be a quarter. Now, these ones are really nice because they're actually not bad values. I'm going to make this one the blue graph, aka the original. I'm going to make this one the red graph, the new graph. And what we're going to do is we're going to plot our invariant points right away. 1 and 1. There's the first invariant point. The second invariant point was at 3 and 1. So that's going to put us to here. Excellent. Now let's sketch in our blue graph. It's at 0 and 4, which puts us to here. We have 1 and 1, so one of the points will be right here. We have 1.5 and a quarter, which is going to be roughly about here. We have 2 and 0, which means that's our x-intercept, aka our NPV. We have 2.5, which is, it's saying undefined, but in this scenario, it probably should just be a quarter if we're thinking about this thing being symmetrical. So I don't know why it would block us out there. So this should be a quarter. And then obviously we can make an edit if we need to. So this will be a quarter. Our next point will be 3 and 1. So it's going to be through the invariant point. And then we're going to go to 4 and 4. So that's going to put us up to here and here. Awesome. Okay, I'm going to sketch the line over this. So we're going to do this. There we go. We're going to do this. Perfect. And that's a little narrower than it should be. So I'm just going to kind of fill that in here. Now, again, on these graphs, what you can always do is write your y equals f of x, just indicating that it is the original function. Now what we want to do is we want to sketch in the reciprocal function. So I'm going to go at 0, it's a quarter. Remember, if it's a large y value originally, it's going to be a small. So 0 and a quarter. We're going to write in 1 and 1, which is our invariant point. We're going to write in 1.5 and 4. So that's going to put us to 1.5 and 4. If it was a small value, it bounces up. Our next value is going to be where at 2, it's undefined. Reason is because there is a vertical asymptote at this point. So if we wanted to, we could sketch in that vertical asymptote. In fact, I would almost make that your first step anyway, but that's okay if you don't. Vertical asymptote where our x value is equal to 2. Okay, so we have our dividing line. Across this dividing line, we have, if I go from 2 to then 2.5, we're up to 4. So it's going to look very symmetrical on the other side. We go from 2.5, which put us to 4. We go 3 to 1, so that's through our invariant point. We go to 4 and a quarter, which puts us down to here. And in fact, I probably didn't even need the table of values because here's what you should realize. Again, if it's a very large y value, then it's going to become small. If it was a small y value, then it's going to become large, and it goes up this way. Because a reciprocal is quite literally just taking the opposite of that value, or the reciprocal meaning its inverse. Okay, now I'm going to go up, 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 like this, and extend to positive infinity this way, extend to negative infinity in terms of the x's. In terms of this side of the graph, I'm going to cross through and then extend up like this. I'm going to extend to positive infinity in terms of x's, positive infinity in terms of y's. And there's our new graph, which again, we're going to call y equals 1 over f of x. I think it is very important to write that in there, just so that I know you understand which graph is which, and that definitely helps. Now we're going to describe our domain and range. Our domain of the original graph was simply that it could be anything, but when they ask you for domain and range in this unit, please don't just be like, oh, it's of the original graph. They're specifically asking you to describe the reciprocal graph's domain. The only restriction was that the domain had to account for that vertical asymptote. In this situation, it was x such that x cannot equal 2. As long as it wasn't equal to 2, it could be any real number in the plane. The one that we're missing here in terms of y's is, again, in our unit and in specifically Math 20, we're not going to deal with a horizontal asymptote that typically is anything different than being y equals 0. It would be very rare if we did, but at the 30 level, they definitely play around with that just a tad. As you might shift a graph around, and when you shift a graph around using more complicated polynomials or complicated rational expressions, it might shift where this horizontal asymptote is. So if we know that it's not going to be equal to 0, I want you to write range where we say that y such that y cannot be that 0 value, and as long as it's not that 0 value, then it can be any number in the real plane. And in fact, actually, when we look at this, we need to be a little more specific on the y's. We know the x's don't account for the x being equal to 2, so we're like, okay, that's fair enough. The y values, do they go any below the y-axis here? No, and in fact, they're only above, and I should say they're only above the x-axis. If they're only above the x-axis, that means we actually need to use an inequality and say it's greater than 0. And maybe, let's define it as that instead. I think this will probably be better, is y must be greater than 0 and not include 0. And once it's past 0, it can be any number in the real plane. This is going to be a way better description of it, because the y values, if I said it just wasn't equal to 0 and it's all real numbers, that implies that it's also negative y values, which isn't true. There is no y values on the red graph that are down here, so we don't want to consider that to be true. All right, that includes all our components here. So again, we always define what the reciprocal function is, state its MPVs from its factored form. The invariant points always come from where y is equal to plus or minus 1 in comparison. And you can use the original, the reciprocal, whatever, because we know that if it's an invariant point, it's the same for both graphs. Your horizontal asymptote comes from the idea that we say, hey, no matter how large or small x is, it will never be 0. Or it will never lead to where it crosses the x-axis, I should say. Where we have our vertical asymptote, it's your non-permissible values. So that's a nice translatable factor. And then when we're trying to build out these tables here, don't put the pressure of yourself or on yourself to just put them all into your calculator. What I recommend is don't do these things. And I shouldn't phrase it in that way. I should say you want to prevent yourself from doing these things algebraically and trying to like plug them quite literally into your calculator. What you want to do is you want to plug it into your graphing mode and get this table of values because it's going to save you tons of time. Okay. Now, we're going to look at one last example, which is what if we have no zeros? So we've now dealt with a linear line, 2 zeros in a quadratic function, 1 0 in a quadratic function. What if there's no zeros? All right, reciprocal of this function. They give us y equals x squared over 1. We're going to plug this in as the following. It's going to be y is equal to 1 over the x squared plus 1 1 over x squared plus 1 as such. There we go. Now, in this situation, is there any MPVs? No, because there's nothing that would cause the denominator to become 0 because it's a squared value, and a squared value is going to make sure that there's no negative that would cancel this 1. So we actually have no MPVs. Okay, interesting. The first time we've had that. Invariant points, we want to set it equal to the original. So we're going to go 1 is equal to x squared plus 1. In this situation, if I subtract 1 from both sides, it's x squared is equal to 0, meaning x is just equal to 0 for the invariant point, and there's only one of them. So that's kind of interesting. It's like, okay, we have 1 and 0, or sorry, 0 and 1, because we want to put the x first. So we have no MPVs, one invariant point. Interesting enough. Let's create our table of values. We're going to go to our graphing calculator and clear out the 2 that we're given. We're going to put in our new ones, which are x squared plus 1, and then the reciprocal of that, which is 1 over x squared plus 1. Graph, there we go. And whoa, okay, interesting. We're seeing a kind of an interesting pattern here. What I want to do is I want to go down to this and be like, let's get our table of values by going second table. We're going to plug in all the values we here see starting at 2, so or negative 2. I'm going to go down to this one here, negative 2 and 5. So this puts me to negative 2 and 5. We have the reciprocal of that, which is 1 over 5. If we go to negative 1, this is 2. Reciprocal of that is 1 over 2. If we go to 0.5, 0.5 is going to give us 125, which is 5 over 4. So I'm going to write it as 5 over 4. Reciprocal of this is 4 over 5. If x equals 0, we have 1 and 1, which was our only invariant point, actually. So let's make sure we highlight that. One invariant point here, and I'm just going to make sure it doesn't bleed into the second category here. There we go. I'm going to go to my table of values and go to 0.5, which is 125, which is 5 over 4 again. There we go. And I just want to make sure that I wasn't copying from the other one earlier. So 0.25, this one is going to give me 5 over 4, which its reciprocal is 4 over 5. When I have a value of 1, this is going to be, let's scroll up here, 1 is 2, which means the reciprocal is 1 over 2, or 0.5. And lastly, if it's 2, it is 5, which its reciprocal is 1 over 5. Awesome. Okay, let's do what we've done before, where we plot one of them in the blue, one of them in red, and then we're going to make sure what these look like. So if I'm at negative 2 and 5, unfortunately, that's going to be off the graph. So I'm going to start it where, and let's make sure, you know what, we'll plot it in there. Just even if it's slightly off, that's okay for me. So we're going to put it somewhere up about here for the first point on the blue graph. The second one will be negative 1 and 2, which puts us to here. We then go to negative 0.5 and 5 over 4, which is like 1.25. And I'm going to be somewhere about here. There we go. At 0, it's 1, which puts me to here. And then the nice thing is everything's just symmetrical about that. So I'm going to go to 0 0.5 and 0.25 here. I'm going to go on to the other side, which is 1 and 2, which is here. I'm going to go to 2 and 5, which puts me somewhere off the graph here. And then what I'm going to do from there is I'm just going to fill this in and go, if I draw in the parabola, arrows up like this, it crosses through all the points, I draw it up there from there. Now, this is going to be where we have y is equal to our f of x, which is our original function. We then want to just draw in our reciprocal function. The reciprocal function comes from the idea that we take all these values and we essentially flip them. So if I had on the original graph, let's say this was y equals 5. The reciprocal of 5 is 1/5. So at that same x value, I go down to -2 and 1/5, which puts me to here. If I go from positive 2y and x equals -1, if I do the reciprocal of -2, that's going to put me down to 1/2, which is here. Reciprocal of 1 is 1, so this becomes an invariant point here. If I take the reciprocal of 5 over 4, well, that's 4 over 5, so that puts me just somewhere about roughly just slightly lower. And I should actually do the same thing over on this side here for that point. So slightly lower, slightly lower. If I take the reciprocal of 2, again, it's 1/2. And then if I take the reciprocal of positive 5, it's 1/5. And so all of these points, if you look at them, large values become very small values. The larger values become just slightly smaller in this situation, or in this case, flip. Now, I'm going to draw in my curve here, and it's going to be the following. If this graph extended, or this original blue graph extended to the left and right to infinity, all of these values would just get less and less and less, and they would tend closer and closer to the x-axis, and the graph would actually look like this. It kind of like makes like a little bump, and then it goes back down flat to the x-axis, and it gets closer and closer and closer as we go. So this is that pattern here, and we're going to consider this to be where y is equal to 1 over our f of x. Okay, now again, with this graph, the interesting thing about it with no zeros is when there's no zeros, there is no NPV. No NPV means, yes, there might still be an invariant point, but there's no vertical asymptote in this situation. So on this graph, I'm not going to draw in some line that would divide this such that I can't cross that verticality. But what I still want to do is make sure we're maintaining our horizontal asymptote, because our graph will never cross the line y equals 0. And I'm just going to make sure I sketch that in here. Our horizontal asymptote, or HA, is where y is equal to 0. As you can see, no matter if it's the blue graph or the red graph, but more importantly, the red graph, even if it gets very, very close to 0, it still will never cross. And that goes back to our principle that we discussed very early in this lesson that said, if I take a really large x value and I plug it in, it's going to lead me to an output that may be super large. But if I take the reciprocal of that, it would still be something that is non-zero. We're not going to have a situation in this section or in our grade 11 content typically where we would have a horizontal asymptote other than y equals 0, just because of this idea that it can only go to this point where it's either going to diverge away from the x-axis or get very close, but it never will actually hit that, or else we would lead to some sort of undefined function in this situation, which we don't want. All right, now asymptotes, we want to just reflect on that. Again, we have no vertical asymptote, so we can write in VA, just none. We want to reflect on the horizontal asymptote, which is where y is equal to 0. Our domain for this one, or D, is where we have x such that x cannot be, well, there's no restriction on x actually, because it can go to the left and right to infinity. Perfect. The range is where y such that y can be any number but 0, but specifically has to be greater than. So we're going to write that in as well here. It can be greater than in this situation. And we actually might need to be more specific. This might be our most specific case. Y is specifically contained between the section of being above 0 and then less than our invariant point, which is 1. So I'm going to write it in as the following. I'm going to use some inequalities to help me out here. 0, which y has to be greater than 0, but it's less than or equal to the invariant point. And as long as it's between the invariant point and 0, that graph will go really flat and be between these two values, but it can be any number or any sort of real number between these two specifically. And let me make sure I write my range in here below because I condense them together, but realistically, it should be tucked below here. Awesome. And I'm just going to, what I'm going to do is because I had the space here, I'm just going to shuffle this into here to be neat. I'm going to shuffle this one in here, and then I'm going to shuffle my range in here. Not saying you have to do that. If you've already written them where they are, you're good. Perfect. Okay. This is where you're going to want to go to your assignment. And again, I would highly recommend having graph paper. I have some in the class for you. Grab a couple sheets. Make sure you're drawing these things on graph paper because you want to be as accurate as possible. And without graph paper, sometimes these can be very tough to draw in.